All right, so there's a ball swinging from a rope around a pole, and we're trying to figure out basically what is the tension on the rope. And so what we need to consider is that a couple of things. This is a circular path. The ball's going to go around there. So you could think of it, and they give us a lot of information. They say that it has a velocity v, right? So we can think of it in terms of this. Because it's a circular path, there's going to be a radius r, and so that would be from the pole out to here. Another thing I want to point out is that it's a right triangle. So this is like the hypotenuse of the right triangle, and then this would be like the opposite. Another thing that I'd also like to point out is that the tension in the rope has a magnitude of L. Okay? And what that means is that it's going to have a y component, right? Gravity's going to pull it down. The mass of the ball will pull it down too. So that'll be like a tension going down. And then it also, because it's swinging outward, will have an x component. Okay? So this is like, this is your total tension force. And this is like the force in the x direction. And this is like the force in the y direction. I should also point out that F of t times sine of theta is going to give us our x direction. Okay. So the horizontal component of the tension can also be calculated based on the centripetal acceleration of the ball. So remember that centripetal acceleration goes from the outside of the circle towards the center of the circle. And also remember that the centripetal acceleration is equal to the linear velocity squared over the radius of the sides of the circular path. Whew, that's a lot. So what I need to do then is just kind of start plugging some stuff in. So I want to know the tension of the rope. So the tension of the rope has an x component that I'm going to try to focus on. And that will be equal to the mass times the acceleration. Okay? Well, if I want to focus on the x component, I would say the force of the tension of the rope times sine. Well, let me write it this way. This might make a little more sense. Erase this. This would be the force of the tension of the rope times sine of the angle theta, right? That would be the x component because it's the opposite, right? Do you guys get that? This is where theta is. Sine would be, it'd be down here. This is the opposite side. That's why I said that. So that gives me my x component. Now, sometimes we say sine is y, but just the way the whole thing's set up, it would be x in this case. And then over here, it'd be my mass times my centripetal acceleration. They should be equal, right? Because the ball is trapped in the circular path. It's not going out further. It's not going in further. So they would be equal. So the circular path doesn't get a larger radius or a smaller radius. They should be equal. So then I'm going to plug in velocity over the radius squared. So far, so good. So now, what is the actual radius of the circle? Well, the radius of the circle is actually this right here. If we think of this as the radius of the circle, right? That's the radius of the circle. The radius would be equal to the length L times sine of theta, right? Now that's just trigonometry. So I'm going to plug that in here on the bottom. So in the next step, I'm going to say that the tension times sine of theta, which is in the x direction, is equal to the mass of the object times the velocity squared all over L sine of theta. But the question was, what is the tension? So then I'm going to subdivide this by sine of theta. and then that means I would divide over here by sine of theta. These cancel, and I get the force tension is equal to the mass of the object times the velocity squared all over the length of the string times sine squared of theta. And that's it.